Okay, great. I think we are live now. Okay, so welcome everyone to this second lecture for masterclass number 3. This is the masterclass about umbrella sampling, and my plan for today is to just scroll the solution together with you and execute it because it's actually pretty fast to run it again. But I'm really happy to stop and to discuss with you to hear from you exactly what you did and where you did it differently from me, and also we can try some different paths if you have ideas while we go through the solution. Okay, great. So I already shared on the GitHub repository for the masterclass the notebook with the solution. So if you want, you can download it, but that could be useful if you want to scroll back and forth while I'm explaining, but my recommendation would be anyway to try to follow what we are doing here. So let me share my screen now. So share screen. Here it is. So you should be able to see my screen now. And here in this tab, I have the assignment. Let me make the fonts bigger. Great. And then in this other tab, I just opened a notebook that, as I said, it's already available, and you can have a look at it on GitHub. So let's see. So the first, the exercise number 0 was to set up PLUMED so as to be able to to install actually GROMACS as well, not just PLUMED. So how many of you did it or had troubles in this part? Okay, so maybe the right question is, how many of you had troubles at this stage and were not able to install the software? I see that there is a hand raised from iPad. I will lower it, okay. So just raise your hand if you had troubles at this stage. Okay, I don't see any hand now. Hopefully this should be easy enough.
I had a problem with installing something, but not with the GROMACS. I had a big problem with WAM for Python.
See. I see. Okay, good. So let's see that later, maybe when we will go through that. But yeah, in principle, you don't have to install anything. The script was provided within the notebook.
Yeah, but my Python couldn't find the module.
I see. Did you execute it? Did you execute your Python from the same directory where the script was?
I guess so. Oh, is it a script that has to lie exactly in the same folder? Okay. Then that's maybe the problem. Thanks.
Yeah, that's possible. Yeah. Yeah, I'm always confused with the way Python finds modules, and but if you put a file in the same directory, typically it's found. Otherwise, you can also add arbitrary directories to the path that Python is searching.
Okay, thanks a lot.
Okay, good. So the first point was just running an unbiased simulation with PLUMED. That's, I mean, that's not difficult. It's just running a standard GROMACS simulation. So these exercises are made with GROMACS, and I think that most of you have used. Sorry, I see some comments. Okay, so if you have questions, it's better if you just switch on your microphone, because I probably will not look at the chat. So in this class we are using GROMACS, and I think also in the next classes you are going to use GROMACS. That's just an example. You should be able to do pretty much the same using any MD code that is compatible with PLUMED. And so this is just for simplicity to have everyone using the same code, but we will really not spend much time into really understanding how to tune the GROMACS options and so on. The only thing that we need to play with is the name of the files. And here it should be clear how to read a given input file, PLUMED input file, and how to generate a given trajectory here. Okay, so let me go to the solution now, and I will execute it step by step and comment it. So I'm just importing some modules here, and I just defined some very dummy function that I will use from time to time in order to clean up the backup files. So this is something that is always tricky the first time you use GROMACS and PLUMED. If you run many examples on the same directory, at some point, GROMACS and PLUMED start to complain because they cannot backup files anymore. So in this way, we can clean up everything. Okay, then the first point was just to prepare an input file that here is already in its final form. Let's see what was the assignment. There were a lot of fields here. So I don't know if I should ask you, as my friends were doing, how to fill this, because we have the solution on the other tab, but maybe I can ask you if you did it in the same way that I did. So here I'm picking the atoms using these shortcuts. So did you do it in the same way, or did you do it differently?
Yes, the same way.
Okay, great. So you know that you can also specify atoms by numbers, and that's the most general way, but this is more convenient because we within PLUMED we have some parser that can understand some useful specific strings here. Okay, and then in the assignment, let's see if there were other critical parts. Here, the histogram, we were going to, I mean, this was very similar to what you have done with Gareth already. So I don't expect any problem here. One interesting thing is that that I think with Gareth you have not seen is the fact that here you can also feed like strings like pi, meaning like 3.14, and also more complicated stuff like pi divided by 2 or something like that. Here, the maximum range allowed, the range allowed goes from -pi to +pi. So the correct way to fill this was to +pi or pi. Again, this was very much the same that you were doing with Gareth. The only difference is that here we had to specify exactly how frequently to dump the grid, because apparently PLUMED is not able to do it at the end of the simulation. And then here you have to modify this to write phi and psi on a specific Colvar file. So that's how I did it. So comment, questions, anyone who didn't manage to do this? Okay, so we'll just execute it. And then in the next cell, I just run this. Instead of running with this percentage bash command that also Max was using, that I'm using a lot in my everyday routines, I'm using subprocess. The reason will be clearer afterwards. It's pretty much the same. It's a bit more complicated, but just to tell you how it works, you can give a command, but you have to say shell equal to true, which means that this string is interpreted as a shell command. Otherwise, by default, it doesn't do what you expect. By default, you should basically pass multiple arguments, one for each of these words. It's a bit more complicated. Anyway, with this shell equal to true argument, it basically behaves the same as our percentage bash cell that you used last time. So now the simulation is done, I think. Return code equal to 1. Sorry, wow. We already have some troubles. Let's see what's happening. Let me see what's happening. Maybe I didn't load the correct module. Okay, sorry, maybe I didn't load, I didn't open the correct, let me reopen the notebook with the correct. Let me kill this. Okay, Conda activate. PLUMED Masterclass. Great. I was using a wrong environment where the correct version of GROMACS was not installed. So let me go again through this. And now this is running. Okay, it will take a few seconds. Great, return code equal to 0. Great, so let's see what's next. Here there is some suggestion about how to analyze your trajectory. So I don't know how familiar you are with Python. I would really recommend you to learn how to use these basic plotting tools because they are very convenient. So did you manage to just copy and paste it? Did it work?
Yes, it worked.
Okay, the very nice thing of Python is that you find a lot of documentation on the web. So basically, if there is something wrong in my scripts, you would be able to find the solution easily. Or if you want to change them and make the plots nicer, it's easy. Okay, so I think this box is really just a cut and paste of what I was suggesting. So let's see the graphs that come out. Okay, so the first one is phi and psi actually as a function of time. There's an error in the legend, in the axis label. So the blue one is phi that is negative, and the orange one is psi that is positive. And then here you see phi against psi. You see that there are basically two basins here, one here and one here. And here you see the free energy shown, computed just as the logarithm of the histogram, shown as a function of phi. There are two clear minima. At negative phi, they correspond to basically these two values of phi, around minus 2.5 and around minus 1.5. And these two minima at positive value for psi around 1 and 3. Okay, good. Any comment? Any of you found something different or had troubles at this stage? Just ask, switch on your microphone. Okay, I think this should be quite easy, this step. So let me see the comments that I noted. Okay, there are many transitions here. You see, this picture shows that the transition between one of the minima and the other is an activated event because you see that the trajectory is kind of stable in one of the minimum, and then suddenly you have a transition, and it's stable for many steps, and suddenly you have another transition, right? Of course, these transitions take such a short time that they are not really to be considered as rare event on the time scale that we are simulating. That is, if this is time, this should be time actually. And so this should be 400 picoseconds. So on this time scale, these events are not rare. And so it's actually not necessary to increase their frequency. They are already sufficiently sampled. But still, this is the typical picture that you see when people speak about rare events. The system is fluctuating somewhere and then suddenly jumping somewhere else. What's special of this is that the time required for the transition is much shorter than the typical time the system spends into one of the minima. Okay, great. Another interesting thing that you can see is that, so remember what we discussed last time. We need collective variables that can distinguish metastable states. Here we have two metastable states, even though they are metastables for with a very so they require a very little time for the system to jump from one to the other. But you see they can be distinguished either using phi or psi equally well. So basically, any transition on phi is accompanied by an equivalent transition on psi. Okay, great. So now point number 2, let me scroll down. Also here, there was an example. This was a bit more complicated because there was more stuff to fill. Hopefully, most of it was just to be copied from the previous point, so not too difficult. So let me go through my solution. Let me show you what I did. So the first part of the file basically is the same as from the previous simulation. Okay, so first, what was the assignment? The assignment here was to run a biased simulation. So instead of just analyzing on the fly an unbiased simulation, what we do here is we add a bias potential. And here you see that the special thing of Plume is that you can really define arbitrary potentials and add them, and they will be felt by your simulation on the fly. So maybe last time you, in the previous lectures, you might have wondered why does it make sense to use PLUMED instead of using, for instance, MD-Trudge for analysis, or MD analysis. They are both very good tools, and they directly work in Python, so you can do a lot of stuff. But the problem with that type of analysis is that you can only do it a posteriori, whereas our plan here is to do something on the fly. So you need something that communicates with MD code while the MD code is running. And that's what PLUMED does. So the main reason to learn all the tricks of the PLUMED syntax and how to use them to define variables is to have basically a unique syntax that can be used both to build variables that you can then bias and to build variables that you can analyze a posteriori. Okay, great. But I think we said that this already last time. So here we have to fill with some custom function. And this requires some browsing of the manual to know that you have to use X to call this variable, to know that you have to specify this periodicity. But part of this was already covered by the previous classes. So let me see if this runs. It's running. Okay, so questions on this point? Any of you didn't manage to complete this or did it in a different way? Just raise your hand or switch on your microphone. Okay, so I'm going on assuming that everyone managed to do this. So this succeeded. And then, okay, I ran already this simulation with the second input file that was called plumed_bias1.dat. And then I'm monitoring it with this, using this script here. Great, this is just a cut and paste of the script in this box. Let's see what's the difference between this graph. Okay, so first, how many of you were able to obtain graphs similar to these ones? Raise your hand or say something. Okay, I see hands raised. Okay, great. Okay, if you had troubles or found something different, let me know. Okay, so what's the difference between this graph and the previous one? So most notably, the system is spending more time in the state with the higher value of phi rather than in the state with the lower value of phi. That's expected, right? We added a bias potential that, let's see again, the functional form is -10 sine of x plus 2. So the sign is becoming positive when x is greater than 2 here. And so -10 is becoming negative when x is greater than -2, sorry. So when x is greater than -2 here in this region, we are going to favor the exploration. So the system is going to spend more time here than here. And so you still see that there is some exploration here, but most of the time is spent on this region of this two-dimensional space. Okay, great. Then we can, let's see how difficult it was. This second part was really similar to what you have done with Gareth. So I hope it was not too difficult. The idea here is to compute the free energy profile with the reweighting procedure, so that you just assign to each frame a weight that basically takes into account how much you favored the visiting of that site. So let's look at these graphs now. So I'm overimposing for phi the free energy. So here the blue one was the original one, the one that I obtained from the first run, the unbiased run, that tells me that the population basically of these two states is comparable, say. Then the biased free energy, the one obtained like minus kBT logarithm of the histogram of the bias simulation, is heavily unbalanced. You see that apparently there is a deep minimum here, right? Once I do reweighting, so I explicitly take the bias into account, and I tell to PLUMED, okay, look, when you do the histograms, basically, you have to weight states here less than states here, because the system was encouraged to go here, so it's less important if it went here rather than it went here. And so once you do that, basically the histogram, the weighted histogram here becomes more heavy, and so the free energy becomes more negative, so less positive in this case. So basically the green line here, you see, it's just it's similar to the orange line. It has the same kind of fluctuations, but it's shifted down here so that the two minima become more or less comparable. So one interesting feature here is that even though the overall free energy here in this minimum and in this minimum is kind of comparable, I clearly see that this minimum is kind of smooth, whereas here there are a lot of fluctuations. So can you guess why? Do we have some interpretation for this? Anyone wants to answer?
Because we have less sampling there.
Exactly, that's correct. So we have less samples here, and so we have less beans that are populated, and more noise in general. It could be that some beans have zero population. Actually, this histogram is done with the kernel density, so should be smooth anyway, but maybe the bandwidth is very small here. So yeah, but the real reason is that here we have less points. So we immediately see this with these strange like fluctuations, non-physical fluctuations in this free energy estimate. But in general, we can expect that here the statistical error will be much larger than here. Okay, and then when we look at the profile on psi, we see more or less the same. The two minima are kind of switched. So the one on the left here corresponds to the one on the right here. So this is the one that is favored in the biased simulation, but then when you do the unbiasing, they are kind of more balanced. Okay, so in line of principle, you would expect the green line to be identical to the blue line, okay? But that's going to happen only if you run a simulation which is infinitely long. So if you are at convergence, they are expected to be identical. But since you have some noise, the noise will be different and the magnitude of the noise will be different. And the green line will have more noise here and less noise here. Okay, great. Comments, questions? Okay, so let's go
I guess
yes.
You will have to find a shift value also, right?
Say it again. So what do you mean with the shift?
So if you're, so it's a free energy, so it's only up to a constant shift in the.
Yes. Yes, that's totally correct. When I say they are equal, I mean up to a shift. Obviously, they are not even similar. There is a shift by kind of 5 kJ per mole, and but I imagine now in my mind to remove that shift, and then they become virtually much more similar. But yeah, the free energy is only defined up to a constant shift. Okay, we have no way using these methods to compute absolute free energy. We are only going to compute the free energy differences. So, totally.
Would you, if you would report this in, let's say, a paper or something, would you then remove the difference in the shift, or would you just report it like this?
It depends on what you want to show. So, if you want to show, so What I typically do is I report free energies shifting the minimum to 0.
Okay. Yeah.
Because that kind of makes sense. It says how unstable is any state compared to the most stable one. Or I align to any reference state that I would like to have. Like maybe if I have, I don't know, 2 objects binding, maybe I want to use as a reference the unbound state. So I set to 0 the free energy of the unbound state. And then maybe my free energy becomes negative instead of positive. But that's more an aesthetic reason. You have to think about what you want to, which is the message you want to convey and how you want to comment the figure. Something that is very important is if you have 2 lines that are almost identical, it's always useful to shift them so that it's you can see both. Here they just came out shifted by some convention that I don't remember now that is used within PLUMED to normalize these free energies. I think there is also an option to set the minimum to 0. If you use it here, and I think it's an option of this convert to FES, and then they would look more similar, basically. Thanks. Other questions, comments? Okay, great. So let's go to point number 3. So the idea here is to play with the WAM. And the first attempt with WAM is this exercise number 3, which is not a prototypical application of WAM that we will see actually in point number 4. But it's anyway very instructive, I think. So let's see how I did it. So maybe let me see first the assignment, if there was something critical. So actually the suggestion was to prepare a new input file identical to the previous one, just replacing 10 with 20. And then just to write files with a different suffix. So it doesn't look complicated. So let's see, this file should be identical to the previous one, but see that here I have -20. And hopefully, if there was no mistake, I'm writing out files which are called, which have a 2 suffix. Okay, so here I just prepare the input file and I run my simulation. It's pretty fast. And here I'm analyzing it again in the very same way, just to see what's the difference. So what I see here is that basically the system is even more encouraged to visit only the second basin. So it doesn't even visit the first basin. So it's always basically in the second basin and never in the first basin here. And now again, I'm plotting the original free energy profile, the one obtained from the unbiased simulation. The orange one is the biased one. You see it's heavily biased towards here. You see, it's interesting here. You don't only see that this basin here is deeper than this one, but it's also shifted. Actually, this is expected whenever you have a minimum and you basically apply a force on it, you expect the position of the minimum to be shifted. You can even predict how much it will be shifted based on the curvature of this free energy and based on the slope of the bias that you are applying here. Anyway, this is consistent. And in addition, you see that it's visiting for some time here, but I guess this is just happening at the beginning of the simulation. No, okay. It's seen a few times. So it goes once here. And yeah, so maybe this state is visited once at -2. So probably this is just a single Gaussian represented in this kernel density. So then I do reweighting. So again, I weight every individual frame with e to the plus the bias applied on that frame, so that if I disfavored a frame a lot, I weight it more. And what I can see is that I obtain the green line, which again is the same as the orange line, but shifted by this sign of x + 2 function. Okay, so again, you see that it has the same ripple here. You see that the population of the two minima now becomes similar. So the two minima has a similar population. I would say this is mostly by chance. So clearly the result goes in the right direction. It's going to relatively make the second minimum less stable and the first minimum more stable. The fact that these two get to the same value of the free energy, I think it's basically luck. And also here I see a similar effect that also analyzing psi, the effect of this reweighting is to increase basically the relative weight of this state. So let me see if this was executed already. Okay, any comment on this? How many of you were able to obtain this? Raise your hand. Okay, great. How many of you had troubles and or obtained something different and want to discuss it? Okay, great. So here are my notes that I prepared just before this lecture. And okay, I basically said already what I wanted to say. Okay, next stage. Now we are going to concatenate our trajectories. This is the typical way I do WAM analysis. There are different ways. You can also analyze the trajectory separately and concatenate the resulting Culver files as you prefer. Then you can find the preferred manner depending on your system. Maybe if you don't want to manipulate huge files, it could be convenient to analyze one file at a time and then concatenate them later. But here, this is fine. So I'm just producing a single trajectory that is called trajcomp unbiased. Sorry, it's called trajcomp cat.xtc. And now I'm importing this WAM tool. So before someone said you had troubles doing this. How many of you had troubles loading the WAM tool? So I see hands raised, but maybe they were raised since before. Okay, so I assume most of you managed to load it. Okay, great. So as I said, it's always a bit tricky to check. At least I find it tricky to check exactly how Python finds the modules, and so especially when I'm loading something that I provided and I didn't install with Conda or pip or whatever, I find it convenient to check where the file comes from, and this is the easiest way. You see that basically this tells you where this file is coming from. This script is pretty simple. We can even have a look at it. I think it might be instructive. Let me open it. So maybe the font is too small. I really invite you to have a look at this and compare it with the equations that I gave you in the slides last time, because it's pretty simple and it's instructive. So the first thing that it does, it rewrites the bias in units of KBT. Then it does some trick that you could at the first exploration just ignore. This is just to avoid overflows. Does the exponential of minus the bias potentials, and then iteratively solve the equations that were in the slides. Basically computes new weights and compute the new partition functions, and so on and so forth, until they are kind of equivalent up to some degree of accuracy. And then it stores the result in a dictionary. Also, this is very convenient in Python to use dictionaries so that you can return objects that contain more information. So, okay, let's try to use it now. It's loaded. then we have to remember what we have to do. We have to compute the bias potential that would have been felt in each of the 3 simulations, but over the entire concatenated trajectory. So I will use this file to process the entire trajectory. And here I just built these 3 functions, which are, okay, let's see how much, okay, it's not so different from this one. The only thing that I had to do here was to fill in the function, which was -10 sine of x plus 2 and -20 sine of x plus 2, and then to write everything in this biases.dat file. And then run it. And then I read it. And this is the resulting array. So I have time here, phi, psi, and then I have the value of the 3 biases. So this means that the bias potential according to the bias number 1 of the first frame was this one. According to bias number 2 was this one. According to bias number 0 was this one. Actually, bias number 0 is 0, is no bias applied. That was the unbiased simulation. It's not very common to have a simulation that is unbiased in an umbrella sampling protocol. Typically, all simulations are biased. But this is to show that you can also include unbiased simulation. Actually, it's common to have unbiased simulation when you do replica exchange. And we will see in masterclass number 5 how to use WAM to analyze replica exchange simulations. And in that case, we will include simulations that are unbiased and simulations that are biased, similarly to what we have done here. So how many of you were able to arrive to this point and produce something like this? Raise your hand or say something. Okay, if you found troubles.
I might have a question.
Yep, go ahead.
So this might be a very stupid question, but
no, there is no stupid question. Don't worry.
But so last week with Gareth, we spent a lot of time on like a lot of emphasis on correlated data, and how to compute, you know, observables, collective variables from correlated data, and how to do this block analysis, block averaging and stuff like that. Are there similar problem with WAM if you use correlated data, or doesn't it matter?
Totally. Yeah, actually the problem of correlated data is appearing whenever you generate your trajectories using some Markov chain process.
Yeah.
And here we have a Markov chain. Actually, we have 3 Markov chains, and data are correlated. You don't see very much the correlation here because maybe the stride is large enough, and it looks like every point is independent from the previous one. But actually, they are correlated, and that's critical to compute error.
Yeah.
Okay. So we will see when we will compute.
Thinking, yeah. So we're doing the error with bootstrapping today, or we might do that.
Yeah, we will do it with bootstrapping, and I will. Yeah. So if I don't, okay. I will answer to your question later.
That's fine. That's fine.
If I don't, raise your hand again. But I should, because it's a very important issue. So far we are completely ignoring correlations, and we are assuming our samples to be uncorrelated. That's fine if you just want to compute averages. Okay, so now we have our bias data frame. I learned since a few months to use these pandas, and it's really, really useful. And then we use this WAM script. Let me see how much we're helping this. So basically it's copy and paste of this. So I guess you were able to do it. Let me just run it. Take a few seconds, only 38 iterations. So you see this W is a dictionary containing a lot of stuff. It contains these partition functions estimated for the 3. This is the logarithm of the partition function estimated for the 3 bias potentials that we are using. So for the 3 Hamiltonians that we are using, actually these partition functions are obtained up to an arbitrary multiplicative constant. So these logarithms are defined up to an arbitrary shift, but what matters are the differences between these. And these are the weights, and these are stored in logarithmic form, so that you have to take the exponential in order to know the real weight of each frame. So you see, this is a much longer array. There is 1 element for each element of your trajectory. Here I'm going to plot the weight as a function of phi. You see that the weight is basically a function of phi, is a continuous function of phi. The fact that it is continuous is not so important. What is really important is that if 2 frames in your trajectory have the same value of phi, then they will receive the same weight. Okay? Why is this happening? The reason is that phi is the only variable that has been biased. Okay? So what we are basically assuming is that the distribution on variables, let's say, orthogonal to phi, is going to be correct from the one that we obtained, that our simulation is going to be correct. What should be corrected is only a posteriori by this reweighting is only the relative population of different values of phi. So that's why the weight only depends on phi. Indeed, if I plot the weight as a function of psi, I see some plot like this one, which is much more scattered. Maybe I should have plotted also, and I will add it right now, the weight as a function of the number of the frame, because it's instructive. So these are first frames and last frames. So basically what I see here qualitatively is the first third is the first trajectory, the second third is the second trajectory, the third is the third trajectory. So we said last time that the weight of each frame does not depend on from which trajectory the frame originated from. It depends only on the value of phi. But then clearly different trajectories are exploring different values of phi. And you see that the weights are typically different from the different trajectories. So, and in particular, you see that there are frames with a weight very high originating from the first trajectory. These are the frames that are placed in the first minimum. This minimum was observed only in the first trajectory. So to obtain the correct statistics, they have been assigned very high weight. Whereas the second and third trajectories explore frames that are less important actually in the unbiased distribution, because they are, and they were only seen because of the bias potential. I don't know if this makes sense or clarified something. Any questions, comments? Okay, so a thing that I like a lot of these pandas is that of using pandas with Plumed is that you can also edit files. Like I can add a new column to this data frame, and there will be this new column called the log weights. This was explained in the structure, yes. So I'm just commenting it. So now there is a new column, and I can write it. Let me execute it to make sure I'm doing things right. But then let me also open this bias.wam file. And it really looks like a normal Plumed file produced by Plumed, but it has been saved by Python. And you see it contains an extra column. That's very useful, because then you can read it back with Plumed and you are sure that all the format will be correct. Okay, great. Then I have to produce a new input file to read it. So now this file now contains also the logarithm of the weights, and I can analyze it in the same way as I think you were analyzing trajectories with Gareth. So I'm just going to read the value of phi and psi from the same file. And then I'm going to read the weights as well. So let's look at the provided template. So you were supposed to fill this. That's very similar to what you did with Gareth. and then all the rest was already provided. So hopefully you managed to do it. Let's see. And then I run the driver on the resulting trajectory. So before I used the driver to compute which would have been the bias potential applied in each of the simulation over the entire concatenated trajectory. Then I used WAMP to compute the weights. And now I'm just using PLUMED again to analyze the simulation, just to produce the same types of plots that I did before. This is convenient because PLUMED does these histograms in a nice, smooth way, but you can use any other tool to do it. So let me run this. Okay. And then I again use a script that was not provided here. Okay, no, it's provided. Great. So, and it's very similar to the ones we used before. Okay, so let's see. This is my concatenated trajectory. You see, first unbiased trajectory, visits both minima. Second trajectory, mostly visit the second minimum. Third trajectory, basically only visit the second minimum. And then you see the reweighted free energy. The green one is very similar to the blue one. You see it has the correct shape. It even has the same ripple as this one here. The reason is that basically the statistics here comes from the unbiased simulation. Whereas here the statistic comes from a mixture of the unbiased and the two biased simulations. Okay, you can see that it's a combination of also the other simulation. It contains some feature here that probably would not have seen in the unbiased simulation. It's not so interesting here, but yeah, clearly the statistics also comes from the bias simulations. Okay, great. Comments, questions? How many of you managed to arrive to this point? Okay, great. A good fraction of people. Any of you that didn't manage to arrive here and wants to ask something? Okay, let's go to point number 4. This is probably the most interesting point, because this is a very standard protocol to use umbrella sampling. It is a very standard protocol to enhance transitions, and that is analyzed using umbrella sampling and WAMP. So the idea here is that it's actually very difficult to build a bias potential that does what you want. And so it's much more common to build bias potentials that do what you want in some narrow window, and then build your list of potentials so that the windows are overlapping, and exploit WAMP in order to take the combination of all your trajectories. Okay, so great. So here there was already some suggestion about how to set up the simulations. 32 equally spaced simulation between -pi and pi. There was an input file to fill here. And I'm just producing all the input files with a script. And here, that's the reason why I'm using this subprocess.run, because in this way I will be able to run these simulations in parallel using Python. So while they run, because it will take a few seconds, I will show you how it works. This is something very useful. If you start working with notebooks, and I kind of became addicted in the last year or so, I think this is a very useful feature to learn, these concurrent futures. This allows you basically to submit stuff in the background, and then you can wait for them to be executed. And it's very flexible. You can check for the documentation. You can do a lot of stuff. I will just comment this example. So what I'm doing here is I'm opening a context here. with this with statement. The reason for opening a context here is that in this way, I will make sure that Python will not leave this cell until all the simulations has finished. And I also say to this that it should run at most 4 simulations concurrently, because my laptop has 4 CPUs, so it doesn't make sense to run many more. And then I will just submit 32 simulations. And each of them is run with a command that is very similar to the one that I suggested here. There is only a slight change that I made. I use this -def fnm option so as to have also separate log files. I think I was doing this at the beginning to just check what was happening in the log files. It's not really necessary. The important thing is that we write on separate trajectories, and that's done here. Okay, now it's done. Questions, comments? Okay, now that was very technical. So let's just concatenate the trajectories. I will suggest you to concatenate trajectories in this manner. In general, it's useful to concatenate them in order. So we have seen that with WAM, the order doesn't really matter. But still, it's nice to have them in order so that you can reconstruct from where each frame comes from a posteriori, just for like understanding or like doing double checks on the trajectory and so on. So one thing that is a bit nasty of the default way of in GROMACS when you use multiple replicas, or in this case, if you just append a number to the file name, is that basically the shell will not put them in the right order. So this is the way to have first files from 0 to 9 and then files from 10 to 31 in this case. Okay, so I'm concatenated them. And then I'm again using the same trick that I used before to run my PLUMED driver in parallel. And it's basically the command that I was suggesting here, but run with a script. It will take a few seconds. And here we will analyze the resulting file. Okay, it's done. So what this script is doing is just reading a separate data frame from each of the trajectories. And then what I'm doing, so each file basically contains 2001 lines. So if I split the rows in this way, I will just paint with a different color each of the separate simulations. I could have done the same by reading separately the color files that I produced while running the simulation. This is just, again, a kind of double check to know that my trajectory was concatenated correctly. Okay, so this graph is showing with a different color what each of my simulations is doing. So you see that some simulations are exploring this region, some other are forced to be on the barrier here. And then you have some simulation that is able to explore a second metastable state here. This second graph, it was also suggested here, yes, the logarithm of the weight. This is giving the logarithm of the weight of each snapshot, and you see clear trends. So how should I interpret this graph? At the beginning, I have the weights of the snapshots that comes from the first simulation, the one where phi was restrained to be around -pi. Then I have the snapshots from the second simulation, third, and so on and so forth. And you see that there is some trend. Clearly, the snapshots that come from these replicas here, that are forced to explore this region here, they receive the high weight. Whereas the snapshots from replicas that are, let's say, around 0 here, they receive the very low weight. This is logarithm of the weight. So you can imagine this as the weight in logarithmic scale. This is very low weight. And again, this is higher. It corresponds to the second minimum here in the free energy. We will see it later in the free energy, the projection of the free energy. And here again, I have another barrier. Comments. So how many of you were able to produce this graph? Okay. Any comment? Does it make sense? Is there something strange? So I have a question for you. What are these vertical lines here? Any of you wants to answer?
It's probably the beginning of the simulation.
The beginning of the simulation. Yeah. Yes, that's correct. So you indeed, in this case, it's nice because it allows you to easily discriminate where each of the simulation starts. But clearly, this is a kind of artifact. It says the simulation started here. Actually, it says the simulation started here. Even if there was a constraint, a restraint saying to the system, go here, the simulation started here. Okay, and so this frame at the end will receive a high weight similarly to all the other frames that are located here. Okay, so that means that we will have the frames in this region here visited more often than they should, because we see them a lot of times just at the beginning of simulations because the system was initialized there. But then the trajectory immediately jumps somewhere else. Okay, does it make sense or not? Questions, comments? Okay, so let's try to go on. And now we produce this file to be read by PLUMED, and also this was kind of guided. Okay, up to here. For this one, so you see as we go down in the exercise, there are less and less instructions provided. I hope you managed to do this anyway. So how to produce this input file? This is basically the same thing that we did before. Just one comment I had to add here, ignore time, because otherwise PLUMED complains about the values of time that are stored in this file here. But aside from that, it's basically the same. And okay, I had to play a bit with the name of the files so as to save them, not to override the previous ones. Okay, so now this file here will be used to just read the weights, not just the weights, read, yes, the logarithm of the weights, and also read the values of phi and psi, and compute free energy landscapes using our usual kernel density. So let's see, it's reading and running. And then I'm going to analyze the return code 0. Great. Analyze again with a very similar script the result. Okay, great. So how many of you were able to produce something like this? Okay, great. Someone is clapping the hands. I don't know if the applause is for me or for the other ones who succeeded. So how many of you didn't succeed and maybe want to report the reason for their failure? Or maybe they obtained something different? Okay, great. So you see this? I think these lines here are related to these horizontal and vertical lines are just the initialization condition. It's just that the first frame is the same for every trajectory. So they all have the same initial value of phi, and the same initial value of psi somewhere. So it's not particularly interesting. If you see at the scatter plot here, this is just an overlay of this graph here. This was much nicer because we can see where each of the point comes from. And now we can compare the new profile, the green one, obtained with WAM, with the original one. The blue one, you see, they are kind of consistent, not identical, but they are very similar in this region here. Again, except for a shift, an arbitrary vertical shift, they are very similar here. Clearly, they are very different here. The blue line has never visited this region. So in the blue simulation, we had no way to estimate the stability of this minimum. But in this region, they should match. And actually, I would expect the green one to be more accurate, just because it combined more trajectories, and it was running for a longer time, also limited to this region. What about the orange line? This orange line is the free energy computed just with the logarithm of the histogram accumulated on all the bias simulations. So clearly this is almost flat, almost flat, because we use these restraints exactly to keep our distribution as flat as possible in the phi variable. So that's expected. Still, there is a maximum here and the maximum here. This would correspond to a minimum in the probability also here, and corresponds to the fact that whenever you have a barrier to cross and you try to place restraints to cross it, you will see something like this. It will be difficult to keep the variable exactly on top of the barrier. So there will be a minimum in the probability here. The probability as a function of psi is not flat, because that's not what we enforced. And you see here, the probability is low, because we didn't encourage the system to go here. Okay, good. Comments, questions? Okay, one little more comment. I'm just checking what I wrote here. Is that if you look at the second minimum here, maybe it's even clearer in this graph here. The second minimum is here. And the variable psi is not very good in distinguishing this minimum from this minimum here. Actually, it's good in distinguishing the first and the second minima, those that we have seen in the previous exercises, but not good in distinguishing this minimum from this one. So psi would not be a very good variable for encouraging the transition back and forth from these two regions. And actually, I didn't give it as an exercise, but something that you can easily do now is to redo everything using psi as a bias variable. And you should see that the algorithm just doesn't work. You will not be able to see transitions, or if so, they will not be irreversible. Okay, questions, comments?
Is it possible to do like multidimensional biases?
Yeah, totally. It's possible, and in this case, it would not be very useful, because in the end, phi is sufficient as a variable to go from here to here. But clearly, it is possible, and it's a very common procedure. It's just expensive. Okay. So clearly, if you have to place 32 simulation in this range, it's going to be 32. If you want to do 32 times 32, is going to be
it scales badly.
1,000 and something. So 1,024. So it doesn't scale well. The reason is that in one dimension, typically, let's say you have state A, state B, and you know that you want to explore all the points between A and B, basically. they are all relevant. And here maybe we exaggerated, also exploring the other barrier, which is higher, the one on plus and minus pi. But in 1D it's easy to place these restraints. In 2D, if we don't have any idea, we would place them as a regular grid. We would have a huge number of simulations. Most of them would be useless because they will be in regions with energy that is very high and is not necessary to bridge between the two minima. Also, this simulation has some frames that are snapshots that are taken from a very high energy, like those lying here, but these are required. Whereas if you do a two-dimensional umbrella sampling, basically most of the simulations will contain frames that are not really used at the end. And of course, if you go to three-dimensional, it becomes worse. Comments, questions? Okay, great. So exercise number 5, computing populations and errors. Not just populations, also averages in general. So one thing that I wanted to do, because it's instructive, is to compute quantities that are not just free energy profiles. And the reason is that sometimes people think that with WAM they can only compute free energy profiles, but actually you don't have this limitation. With WAM, you can compute the weight of each frame. And then once you have the weight, you can compute the average quantity of anything. So what I will do now, I will run this, and because this takes a while, and then I will use this time to do comments. So the exercise was to compute a few quantities like population of the metastable B, defined as phi included between 0 and 2. So let's first discuss about the observables that we are computing, and then we will discuss about the error. This is a very important issue. It was raised already. So first of all, observables. So population of state B, the way I'm doing it, I'm defining it. So I'm first reading my trajectory, and then I'm checking when trajectory is greater than 0 and smaller than 2 at the same time, and I define this as state B. So this is in B is just an array which is 1 if I am in B and 0 if I am somewhere else. And is in A is the other way around, is 1 if I am in A and 0 if I am somewhere else. You see that if I put this together, they don't cover all the cases. Okay, 0 is not included in any of them, but that's just a single point. Doesn't matter. Points greater than 2 are not included anywhere. Maybe it could have made sense to include points greater than 2 into basin A. I didn't do it here for simplicity. So a very general rule is that once you have high barriers, the way you define your states, and you want to compute populations, the exact boundaries that you use to define your states is not so important. Why? Because now we see free energies, but as soon as you translate these to probabilities, you have to imagine that the probability here at this point will be very, very low, much lower than here. So once you integrate over basin B, the fact that you start to integrate here, or here is not so important, okay? So it's important, however, that you don't include these. So it's not so important that you include these in basin A, because basin A will be dominated by these two regions here. On the other hand, it's actually very important that you don't include this region here into basin B, because you see that points here have a probability close to these ones. Okay, so that's why I set the boundaries for B at the barriers like 0 and 2. And whereas for the boundary for A, I just said smaller than 0. Maybe slightly better would have been smaller than 0 and greater or greater than 2. Okay. Then let's see the other question. free energy difference between state B and state A. How to do it? I just compute. So, okay, for population of state B, I compute the average value of my is in B variable, weighted with weights that are just the exponential of my log weight. To compute the free energy difference, I just do minus kBt logarithm of the ratio between the population of state B, defined as before, and the population of state A, defined as the average value of is in A, weighted again with the same array of weights. Does it make sense? So how many of you were able to compute averages in this way? I don't see many hands now. 3. Okay. What was difficult? Maybe can you comment something? Anyone who didn't succeed and wants to say why? So let's go to the next point. Average value of angles. So the easiest way to compute the average value of an angle is just to do the average of the angle, but that's not going to work in general. So doing average of angles is very common, and that's why I wanted to put this as a question. However, in this specific exercise, the thing is not so crucial because all the angles associated to the state B are going to be in the range between 0 and 2 by construction, because that's how we define state B. And all the angles associated to state A are going to be between minus pi and 0, again by construction. Okay. However, the proper way to do averaging of angles is not to do the average of the angle itself, but is to use so-called circular averages. And I provided the link down here. On the Wikipedia page is quite clear, I think. So the idea is, instead of doing the average of the angles, what you do is the average of the sine and the cosine of the angles. Okay. That's the same as before. The average weighted with these weights that are exponential of the logarithm of the weight, multiplied by these conditions, so that we know that the average is conditioned to the fact that we are in basing A for this or in basing B for this. Okay, so this is the average value of the sine, average value of the cosine, and then the ratio between these two numbers should be set equal to the average value of the arcotangent. And the way to define circular means is to take the, is the average value of the tangent, is the tangent of the average angle. So the standard way to do circular means is to take the arcotangent of the ratio between these two numbers. Okay, the arcotangent has some not nice property that cannot distinguish between positive and negative signs. So there is this very standard function that is called arcotangent 2. It's called like this in every programming language that I know. So it's a kind of standard name where you provide directly the value of the sine and of the cosine, and it takes the arcotangent of the ratio and also associate it with the correct sign. Let me check what was written here. Minus 1.8. So population is this like 4 every 1,000, so 0.4%. Delta F is 13 kJ per mole, 13.7. I don't know how many of you obtain similar numbers. The average value of pi is minus 1.8 in one state and 0.9 in the other state. The numbers do make sense. Minus 1.9 here and 1.08 here. You probably obtain very similar numbers if you just straightforwardly compute the average of the angle without doing this trick. Comments, questions? Did you obtain different numbers? Okay, so let's see now what's happening. So I'm waiting for the bootstrap to end. It's over now, great. How is this bootstrap analysis working? What I do is I pick 200 samples from my trajectory. I reanalyze each of these bootstrapped trajectories. And the reason why this takes time is that I'm doing one every time. So I do 200 times one. This can be accelerated using some faster implementation of one, but this is reasonable. It only took a few minutes, so it's fine now. So, but what you have here is basically just a copy of this done on this trajectory that I generated by extracting some of my blocks with my bootstrap. And then I compute the errors just doing the standard deviation. This is the error on the population, error on the delta F, error on the two angles. So one question that you asked before is why do we use bootstrap even though we have correlated data? So this is something that always, so I know people are always confused by this because you learn from books that bootstrap is only valid if you have uncorrelated data. And on one hand, you see this, and on the other hand, when you learn how to do block analysis, you typically don't use bootstrap, but you rather use the standard formula to compute the error of the mean. So what you do is you divide your trajectory in blocks and then compute the average of your quantity of interest on each block, and then look at how diverse are these, how heterogeneous are these averages, and then take the standard deviation divided by the square root of the number of blocks as an estimate of the error. So when you think about this procedure, you should think it in two steps. So first, you are doing blocks in order to obtain representative samples that are as independent as possible. And then as a second stage, you use this standard formula for the error of the mean, which is the square root of the variance, so like standard deviation divided by square root of the number of points. So the first part, like doing blocking so as to generate data points that are as independent as possible from each other, is also done here. The second part is done here using bootstrap instead of doing the error of the mean. Okay, so what's incorrect is to do bootstrap assuming that your frames, the frames that you generate in your simulation are independent of each other, because they aren't. You sometimes find the recommendation in the literature to estimate autocorrelation times and then sample points with a stride that is larger than the autocorrelation time. This might work in some case, but my experience is that it's very risky because it's really, really easy to underestimate the autocorrelation time of any quantity. So the procedure that I find the most robust is to take your trajectory, split it in blocks. In this case, I did analysis with 10 blocks, but you can try with a different number of blocks. Then, so let's see what is this doing. So I have 10 blocks. So I take my trajectory and I reshape it. So let's see how. So I first, you see here, first I'm reshaping it so that I have 32, as the first index, I have my 32 trajectories. And the second index, I have the number of blocks. And the third index, I have the frame in each block. So remember in which order was this array stored. So the last index is the index of which of the bias potential was used to generate this value. and the previous index was the index of the frame in my concatenated trajectory. Now I will have this index of the frame that will be redistributed across 3 indexes. So the first, across 3 indexes, yes. So the first index is just the number of trajectories, 32. The second index is the number of the blocks. And the third index is the number of frames per block that I have. Okay, so each trajectory was 2000 frames, so we'll have 200 frames per block. And then whenever I analyze this, what I do, you see that I select blocks based on this random choice. This random choice is done with replacement, so that I might have some time like the same block extracted twice, some block that is missing, so some parts of some trajectory will be missing, some parts will be appear twice or 3 times. I will just flatten the resulting trajectory or reshape it here, feed it into WAM, and proceed with the analysis. Does it make sense? Questions, comments? There's a microphone. Yeah.
Could you please quickly repeat this procedure once? I'm not sure if I have grasped it properly.
So sorry, can you say it again?
Could you please repeat the procedure that you have just mentioned? Repeat.
Yes. So what I'm doing here, I'm just taking my concatenated trajectory. So let's see what happens on the trajectory, which is easier. And then for the bias, there will be an extra index. So let's see what happens for the trajectory. So I read it here. I reshape it as 32, -1. This means I reshape it so that the first index runs between 0 and 31, and the second index runs as necessary. I take the last 2000 frames. Why? I want the number of frames per trajectory to be a nice number and not 2001, a number that can be divided by 10. So I basically am discarding the first frame. Then I reshape it so that I will have 32 trajectories, n blocks, and then 2000 divided by n blocks. This could have been -1 equally. I could have used -1 here. It should have worked equally well. I will not execute it again because it takes time. So what I'm doing, okay, great. So now this CC as, no, I'm making a mess, sorry. Here it is. Okay, now this CC has 3 indexes. The first index is the index of the simulation. The second index is the index of the block. The third index is the index of the frame within the block. Then at every iteration of my bootstrap, I'm picking a list of blocks. Okay, I reassemble my trajectory just using this list of blocks as an index for my array and flattening the resulting trajectory. This trajectory, so let's say that my random choice contains block 5 and then block 7. What I will have here, I will have block 5 and block 7 concatenated from each of the trajectories. Does it make sense?
Yeah.
Yes, yes.
Okay. Other questions, comments? This is very important. So if you have any questions or comments, just ask. So let me say it again, because this is the thing that generates most confusion usually in students. So although Bootstrap is usually used to analyze uncorrelated data, you can use it to analyze correlated data if you before do a blocking. So you divide your data set in blocks, and then you do Bootstrap on the blocks and not on the original frames. Now, why do we use Bootstrap instead of doing something simpler like error of the mean or so? And you have seen with Gareth also how to do the error of a weighted mean. That is also something very useful. The reason is that I want to know also how much my finite sampling affects the WAM procedure. So whenever you have something that is a complicated function of averages, then you could in principle compute the error on your averages and then use error propagation to find the error on the quantity of interest. Now, doing error propagation through WAM is complicated. We would have to compute the derivative of the result of the WAM operation with respect to the presence of some frames of some blocks in its input. So it's very complicated. It's much simpler to just run WAM again with a different trajectory. What's really important is that you don't use Bootstrap on the trajectory directly, but you first do some blocking. Questions, comments? Okay, yes, I see a microphone on.
Yeah, maybe.
Yeah.
So you do this on picking different blocks, and then you make sure they're uncorrelated in the same way as block averaging.
Yeah, I'm actually not making sure. The way to make it sure, it would be to do the same with a smaller number of blocks.
Yeah.
Yeah.
Yeah, you should play with that.
Yeah.
So are they just directly comparable, all your estimates from WAM when it's different block? I guess so. That's just bootstrapping in general.
Yes, let's see. So delta F.
It was just that I think my question is whether the weights are comparable.
Yeah, I didn't save the weight, so I cannot show you that, but I can show you, for instance, the delta F. So the delta F estimated as a function of the bootstrap iteration. You see, they are not so different from each other. They are comparable. Indeed, the standard deviation was 0.4.
Yeah, yeah.
Okay, so if you look at the weights, of course, if you look at the weight for, let's say, frame number 10, it will be different because frame number 10 has a different meaning in the different trajectories.
Yeah, of course. But
okay?
If you tracked all the frames, I mean,
yeah, exactly.
Yeah,
that's expected to. Yeah. Other questions, comments? Okay, my comments now. We are analyzing the full trajectory. Yeah, it's common practice to discard the initial part of the trajectory. It's not so difficult, and actually at the end of this sheet, we have some analysis done discarding the initial part of the trajectory. And we will discuss it. Then, okay, there is this comment on the average of angles. You have seen that this is a bit slow. It can be optimized. And actually, I have different versions of this WAM script where you can, for instance, start the self-consistent equations from the log Z that were estimated, for instance, at the previous bootstrap iteration, or when you did the first WAM calculation using the full trajectory. That probably would converge faster. And also, if you look at this paper, there is a way to write WAM in a form that is not a self-consistent procedure, but it's a minimization. And it's expected to be faster, and it's a bit more complicated to implement, but I tried. It's actually significantly faster in terms of needed iterations. Another comment is this one, that when we are doing, so one of the exercises was to compute delta F. You see at every bootstrap iteration, delta F is in this range. It's reasonable. And what's important is that it's finite. So in line of principle, it's possible that for some of the iteration, you pick blocks such that one of the two states has never been visited. So we know that in the full trajectory, both states have been visited. But let's say that in one of the iteration of the bootstrap, by chance, you pick a sequence of blocks such that one of the states has not been seen. Okay, then the free energy difference will be either plus infinite or minus infinite. That's not good, because clearly the average of an array that has one element that is minus infinite or plus infinite is not well defined, and its standard deviation is not well defined as well. So to cope with those cases, one can implement, one solution is to implement Bayesian bootstrap. And you can just Google for it and find out how to implement it. And also it's discussed a bit in this paper. So it's something that could be useful if you are in corner cases where at some of the iterations you find infinite values and you don't want to be in that case. Okay, other questions or comments? Okay, so exercise number 6. This was like exercise number 4. So most of you, well, many of you raised the hand saying that you have done exercise number 4. So how many of you did exercise number 6? I see 1, 2, 3. Not many. Maybe people were scared by exercise number 5. So exercise number 5 was difficult, but I think it's very important. And I really hope that the fact that it was difficult will not stop you from checking a posteriori how to do it and learn how to do this analysis, because it's really useful. So exercise number 6 is straightforward. It's just, I'm just redoing exercise number 4 with a different topology. So initial structure. So I mean, I will not even comment this. It's just I'm writing files with a different name. I'm running all my simulations. We'll wait a few seconds for those. I'm going to concatenate the trajectories. Once they are done, let's see. It takes some time. Still running. Why is it taking this long? Okay, it's done now. Great. So now I concatenate my trajectories and I just analyze all of them. I'm doing the same as before, just using different file names to avoid clashes and to be able to load again the previous files. So here I'm just recomputing the energy with each of the restraints from the concatenated trajectory. And here I'm analyzing the whole trajectory. So you see it's very similar to before. Also here there is an initial transient. Now the initial transient is different because you see all trajectories starts from the minimum number 2 where phi is positive. So the initial weight now is low. In the previous plot, the initial weight was high, so the points were starting from up here. And then I do WAM again, like before, and I analyze the resulting free energies. And let's wait for the plot to come out. So PLUMED is just doing the plot. Okay, great, here it is. Okay, so now I have, in this graph, I'm putting in blue the free energy as a function of phi from the previous exercise, from exercise number 4. Whereas in red, I have the free energy as a function of phi for exercise number 6. So identical setup, starting from a different initial condition. You see the profiles are very similar, except that this minimum is a different energy. Okay, so this means that that basically the result was affected by the choice of the initial condition. So now this question is for the 3 of you that raised the hand and did the exercise. Did you obtain something like this?
Yes.
Okay, great.
Yes.
Okay, so let's comment a bit more about this. So let's see which notes I took here. Okay, so the first interesting thing is that this is the not reweighted free energy. So this is just basically the logarithm of the histogram. You see they are virtually the same. They are very similar. Clearly they are not identical, but they are, so it's not the same graph plotted twice by mistake, but they are very similar. So in both simulations, I was basically forcing the system to spend the same time at every value of phi. And but in the second simulation, the predicted stability of the second state was slightly higher. Okay, then let's look at this graph here, or maybe we can look at this graph here. Let me maybe open this in a new tab if it works. It does. And then we'll scroll up and compare it with this one. So this is the new graph, and this was the old one. So you see that the region that we explored in the psi variable is actually different. So I'm not here showing the histogram of the phi variable. I suspect it will be undistinguishable. It should be very similar, the histogram of phi in the two simulations. But the histogram on phi and psi, here I don't have a histogram, I have a scatter plot, is significantly different. You see that for this region here, they are very similar, but here there's something different happening. So if I initialize the system in psi, it samples this region here. If I initialize it, if I initialize it in B, if I initialize it in A, when I pull it toward the second minimum, clearly what's happening is that it first jumps here, and then only after some time it finds the correct minimum that is placed somewhere here. Okay, so there's something different in the two simulations, and I can interpret what's happening looking at the variable psi here. But you can imagine in a real case where you are biasing phi, and you don't know what is the variable psi to check. You don't know if there is another variable that is maybe slow or moderately slow that would take some time to be sampled. So it's really difficult to detect this sort of problem in a real situation. That's why I would say in a real case scenario, the most recommended way would be to really perform again your entire simulation starting from a different minimum, which is exactly what I did here. So when I did my simulation again starting from minimum B, I obtained a free energy profile that is kind of different. So as a general rule, what I can say is that what I expect is that if I initialize my simulation in state B, I will tend to overestimate the stability of state B. If I initialize my simulation in state A, I will tend to overestimate the stability of state A. And this is consistent with the finding here. So you see that basically the stability of state B has been underestimated in the first simulation with respect to the second simulation. I cannot say if the second simulation is better than the first one or the other way around. What I can say is that basically the correct value should be somewhere in the middle. Okay, so clearly the orange line would be a kind of upper bound, and the red line would be a kind of lower bound. Comments, questions? Yeah.
Would this difference be avoided if we discard some part of the initial trajectories?
Yeah, that's a very good point. Yeah, I did the exercise specifically in this way so as to highlight this problem. Then you can, here I also did some check discarding the initial part of the simulation. I didn't repeat the full bootstrap analysis, but you can do it. What I did here was just to make the analysis keeping an arbitrary number of frames until the end of the simulation. So if there's not a mistake here, what I'm doing, you have to be a bit careful when you read the trajectories not to make mistakes with indexes. But the idea is just to keep only the last frames in the trajectory. And this function here is just doing the analysis for the trajectory saved with the first protocol and for the trajectory saved with the second protocol. And it's then reporting the free energy difference, computing as minus KBT logarithm of the sum of the weights in state B divided by the sum of the weights in state A, with the same definition that we used above. So this is the analysis keeping the last 2000 frames, which basically means the entire trajectory. And it takes a while because it's doing the WAM stuff. So you see, this is 13 and this is 10. This number should be compared with these differences here. So the number that I've seen, that I'm plotting here, is the integrated free energy on this minimum compared with the integrated free energy on this minimum. So it's not exactly corresponding to the difference between the values in the minimum. But clearly the orange one, which was the first simulation, is higher than the red one by something like, I don't know, 5 or so. And here it's, okay, 3 kJ per mole difference. Now, if I repeat the analysis, only keeping the second half of the simulation, I see that the numbers are getting closer to each other. But still, the difference is larger than the statistical error. Let me try now. I didn't try before, discarding even more. So I'm taking only the last fourth of the trajectory. They are getting closer. Clearly, as you discard a longer part of the trajectory, the statistical error will increase. So you have to find a way to strike.
Why not just combine all the data?
What do you mean? Combine all the data?
I mean, you started two different like starting structures or configurations. Why not just concatenate all the I mean, it makes sense to discard some of the initial, but instead of just keeping on discarding, why not just combine, you know, the data starting from basin A and the data starting from basin B?
Great. That's a very good point. And actually, that's what I would do to have the best estimate of the free energy difference. Okay, that's a very good point. Still, it's instructive to do them separately because this is basically telling you, look, the result depends on how you initialize the simulation. If you have multiple ways to initialize the simulation, you can try to combine all of them. Then how do you know that the relative weight should be the same? So how do you know that the two possible initial conditions are equally good? So if they are both equally good, then it's formally correct to do what you are suggesting, so to combine them. Otherwise, in principle, it could be suboptimal. Anyway, in this case, what we know is that one of the two simulations will overestimate the result, the other one will underestimate the result. So certainly combining them will give a result that is better than each of them individually. Okay, does it make sense?
Yep.
The standard way to do umbrella sampling is to do only simulation from one minimum and discard the initial part of the trajectory. It's very dangerous. I would always recommend you to, at the price of course, repeating your simulation, repeat it starting from the second state. It makes sense in this case if you have two states and you're trying to probe the free energy difference between two states. It could be maybe bound and unbound state for a ligand somewhere or whatever else. But that's really my recommendation. Yeah.
Last time you suggested doing steered dynamics across the potential biases. So if you already done that, I guess you could just start at the minima of your bias for each of your, individual biases. So you always consistently start at the minima with the starting structure also.
So if you do steered MD, actually,
then you have a trajectory there.
So what I did here, I didn't do steered MD, but I just suddenly imposed the restraint. Clearly, I could do steered MD. Still, the result could be different if I start my steered MD from A or from B.
Yeah, but let's say you had 10 different minimas. Like this is a very simple system, but 10 minimas, and you had to choose where to start it in one of those 10 basins. And if you then did steered MD across all the 10 basins beforehand, then you have a trajectory across all these 10. And then you can start 10 times this with a starting structure in each minima of the 10 different basins. And then in some way you're sampling all of it.
Yeah, I think it's fine. If I understood correctly, it's fine. The thing that you have to be careful is basically to, so you should make sure that you're able to have reversible transitions. So you see the critical issue here is that you have the same result both if you start, you should have the same result both if you start in A and you start in B. Okay, so if you steer your system to state B and then apply a restraint that is bringing it back to A, is the A that you reach the same A that you started from? So if you have a few variables to analyze, it's very easy to check. So in this case, it's easy to see that at least, where is the other? Maybe I closed it. It's easy to see that state B that you obtain at the beginning of this simulation is not the same state B that you have at the end of this simulation or at the beginning of the other simulation. In general, it's very difficult to do this type of analysis. So my experience is that umbrella sampling is really tricky to use in practice. So the safe way for me to use umbrella sampling, I will show you in 2 weeks or 3 weeks from now, and is to use it with replica exchange. If you use it with replica exchange, you will be able to see continuous trajectories going back and forth, and that will tell you basically if your variables are able to steer the system through your minima. Otherwise, it's really dangerous. Anyway, a good check is to try different initialization condition and look at how consistent they are. So clearly, in this case, the difference is not so much. One could say, who cares about a difference of even 2 kJ per mole? That's less than kBT. I don't care. That's fine. And in this case, maybe just combining the forward, so the two protocols together, and to have the best possible result, that will be a number within this range, it's probably fine. But if you find a huge gap between these values, then you have to be careful. Other comments?
So it's about the reversibility of the transitions. Because somehow in my head, I think about sampling of the other dimensions, which we saw in one of the previous graphs was also not very good, because if you look at the other degree of freedom, the free energies differ a lot. Is this related, or am I?
Yeah, it is related actually. So here we cannot quantitatively check if the transition is reversible, because we have no transition, or better, we have one transition in each simulation. If they start from A, they go to B once at the beginning. Then, yeah, the point was this graph here was this graph here, yeah. So the reason why, so you would be able to see reversibility or non-reversibility by looking at the simulation bias on phi, and this will be immediate when you analyze, for instance, metadynamic simulation, and you should see this with Max next week. In that case, you would see that a trajectory is not, the system is not able to come back. And that means that your collective variable is not sufficiently good to bring the system back. So in this specific case, I see a discrepancy between the two calculations, but it's relatively small, so it's not a big issue. So maybe strictly speaking, this variable phi is not sufficient to describe the transition, but if you're happy with an error of 2 kJ per mole, is totally sufficient. But yes, the fact that the transition driven by a restraint in phi is not reversible is related to barriers present in orthogonal degrees of freedom. Because phi always does what you want. You have a restraint on that, you can easily monitor what it does. But what you cannot monitor in general is what all the other variables are doing. This example is a bit stretched because this variable psi is, these simulations are super short, and the error that is induced by not sampling properly psi is in absolute sense small. But this problem can become serious in other situations. Other comments? I don't want to discourage you in using umbrella sampling and using WAM. WAM is super useful to combine simulations done with different bias potentials. It's well-founded theoretically, but you need to be careful. And usually repeating simulations with different initial conditions is a very safe check. Good. Other questions, comments? Okay, so I've seen that many of you has done exercise until point number 4. And then most of you were scared by this. I don't know why. Maybe the code was not easy enough to read. Any comment on this? Why was this part difficult? So I really encourage you to have a look at this now And hopefully after the lecture, it's clearer how it works, because this is really important. It's very important to be able to compute errors correctly, and this error calculation contains basically all the elements, all the blocks that you need to analyze any simulation. It has the block analysis part, so the trajectory is split in block, and then after you have done the blocks, we do here some fancy analysis that is one. But you can do other stuff here if you need. Okay, good. So if there are no more questions or comments, I think we can close here. So thank to everyone for your active participation. And then let's keep in touch on the chat if you have other questions when you try to complete the exercise. And then that's it. So for, I think, most of you, see you next week.
Thank you.
Thank you very much.
Bye-bye.
Thanks. Bye.
Bye.
Thank you. Bye.
Bye. Thank you.